here with Bryan Catanzaro. Bryan is Vice President of Applied Deep Learning Research at NVIDIA. Bryan, welcome to the TWiML AI podcast.
Thanks for having me.
Hey, I'm really looking forward to diving into our conversation. I've been trying to speak with you for a while. I'm not sure why it took so long, to be quite honest, but glad we're able to connect now. We'll be talking about a lot of the fun stuff you've been working on. But first, I'd love to have you share a little bit about your background. Folks might know you as being one of the founders or creators of cuDNN, the CUDA deep learning library. But how'd you get started in machine learning? What's your story?
Yeah, well, I actually started doing machine learning on GPUs back when I was a grad student at Berkeley, and I published my first paper on how to train big support vector machine models on GPUs at ICML in 2008. Back then, it was kind of exotic to have somebody working on parallel computing and machine learning at the same time, and I kind of got this puzzled reaction from the conference goers, like, why should we care about scale? Because it just wasn't as big of a topic back then. But I had this belief that machine learning and AI was going to change the world, and to do that, it was going to need to have the biggest models and train it at huge speeds. And so that's what I worked on for my PhD thesis. And when I graduated in 2011, I decided to go work at NVIDIA in NVIDIA's research group, and I was in this programming systems and applications group that was focused on trying to figure out like what the future of GPU computing looks like. And I decided that machine learning needed some help with deep learning because it was starting to take off, and this was about the same time that Alex Krzyzewski was doing all that great work with ImageNet and cuDNN, for those of you that remember. And I thought, it's a lot of work to write all of these kernels that we need for deep learning on the GPU. And I know people around research and industry are all rewriting their own kernels to try to train their models faster, but it seems like this is something that NVIDIA could do, and it would be really helpful. And so I started writing this little prototype library and optimizing it for our GPUs and explaining why deep learning might be important to NVIDIA's leadership. And they decided to take my little research product and turn it into cuDNN. So that was a really exciting thing for me to be involved in. And, it gives me great joy to think about, all of the millions of AI developers around the world that have used cuDNN at one point or another. And, all of the great work that has run through these kernels that, some of them I started writing long ago. Now, of course, cuDNN today is a huge team with a lot of people doing really amazing work. And I'm not sure if any of my code still lives on, but it was a great honor for me to be involved at the beginning.
That's awesome. Awesome. And what's your role now at NVIDIA?
So I lead our applied deep learning research team, and our goal is to find new ways of using deep learning to make NVIDIA's products and NVIDIA's work better. And we work primarily in 4 different areas. So graphics and computer vision, speech, language, and then AI for system design. As you know, NVIDIA is a systems design company. We build chips and libraries and compilers and networking hardware and data center style computers. And, at every level of the computing stack, there's interesting opportunities to apply AI. So we work on all 4 of those areas.
Nice. You've also been active, at least historically, in the HPC community. Is that still an interest of yours?
Yeah, I mean, I think that there's a lot of overlap these days between high performance computing and artificial intelligence. And, I've always been interested in trying to do things at scale. Part of this came from my PhD studies. I was at Berkeley, which has a really strong HPC program. And, I worked alongside of really great people like Jim Demmel, Kathy Yellick, who, are sort of really important leaders in HPC, and they kind of made me think about things in an HPC mindset, and that kind of translated to my machine learning work as well. In 2013, actually, I was part of an effort with Stanford, with Adam Coates, Andrew Ng, and a few other grad students publishing a paper at ICML on a commercial off-the-shelf HPC approach to deep learning that I thought was really great. We were able to take the process of training an unsupervised computer vision model from running on 1,000 servers that were CPU based to running on 3 servers that were GPU based. And we did that because of a lot of careful optimization and kind of the HPC mindset applied to deep learning. That was I think exciting work. It kind of reinforced my beliefs that deep learning could really benefit from HPC and from that sort of mindset of like, what's the speed of light and how close can we get to the speed of light when we're trying to train these models.
And we've since seen a lot of development in the field of scaling and distributing deep learning training. Toolkits like Horovod and others in that space. Is that something you're still actively working in?
Yeah. In fact, we have a paper at the supercomputing conference coming up in November on scaling very large language models to large GPU clusters, with many thousand GPUs, and doing so at extreme efficiency. And that's part of our Megatron project. Megatron being the biggest, baddest transformer. We want to be able to train like super awesome, super big transformers on HPC infrastructure, and so we have an open source project on GitHub where we are constantly putting in all of our optimizations and scheduling and better kernels and better networking and all of that. And then we described some of the algorithms that went into that at this paper that's going to be published at Supercomputing this fall.
Oh, nice. Let's dig into that. But I should mention that if you're attending Supercomputing in person, it's here in St. Louis, which is where I'm based. We should definitely meet up, do a TWiML meetup or something like that.
Absolutely.
So it sounds like there is planned to be an in-person component to the conference this year.
Wouldn't that be fantastic? I mean, my goodness.
But in terms of Megatron, tell us a little bit more about that project and its goals.
Well, this project has been going on now for about 3 or 4 years, and it was obvious to us that these large transformer models had enormous potential, and they seemed that the more we scaled both the training set as well as the models themselves, the better accuracy that we were seeing and other people in the community were seeing. And I think that's been now true for quite some time, maybe 3 years or so, that we just keep seeing the records fall as people train bigger models. I think that GPT-3 last year was just very inspiring for the entire NLP community. I'm aware that sometimes these large language models are controversial, and I think that's appropriate in the sense that with great power comes great responsibility, and so we should expect that as we train models to do more and more complicated things, that we have to pay more attention to how they're used, so I'm aware of all of that, but at the same time, there's a great excitement in the community, and many companies around the world in many different industries are starting to use these large language models to solve important problems. And so, when we were looking at that at NVIDIA, first of all, we have our own NLP applications that we're very interested in, and we want to have state-of-the-art modeling to do that. And second of all, we want to show the world, what's possible with a really well-configured DGX SuperPod, right, where we have thousands of GPUs with a really awesome Mellanox interconnect and good software sort of orchestrating the training process of a large model across many thousand GPUs. I think that there was some ideas floating around in the community, maybe 3 years ago or something, that GPUs weren't very good for training large transformers, and I think that's because at the time the software hadn't really been written to take advantage of what we can do with modern GPUs and modern networking to sort of bring to bear the might of something like a DGX SuperPod to train one model. And so that seemed like an opportunity to us that, well, it's time, just like cuDNN was kind of like let's show the world how to train convolutional models on the GPU. For me, Megatron was kind of analogous, like let's show the world how to train very large language models on the GPU at very, very high efficiency. And I'm really proud of what we've been able to accomplish. When we're training very large GPT-3 style models on our DGX SuperPod, we are actually sustaining 52% of the tensor core peak throughput over the entire training run. And 52%, I realize that's not 100%, but if you have an HPC mindset, getting to 52% of peak, especially something running on the tensor cores, which are extraordinarily dense arithmetically, that represents a big achievement, and not just by the Megatron team, but also by all of the people working at NVIDIA on cuBLAS and on Nickel, the communications library, and on the NVSwitch and the Mellanox InfiniBand software and hardware, as well as the GPU and the tensor cores and the caches, and like basically every part of the system is running full tilt. That's really exciting to see. And of course, it has a big impact because training some of these models can take millions of dollars, right? So if you're going to spend several $1,000,000 of compute time to train a single model, then if we can make it go, let's say 20% faster, then that could save you $1,000,000 right off the bat, and of course that could then enable you to do even more ambitious things and hopefully deliver even more value with the model that you train. And so this Megatron project, I think, has been pretty exciting for us to work on because we see it being useful to a lot of people.
And how does Megatron compare to GPT-3? And is it primarily an infrastructure and scaling effort and demonstration, or are there some algorithmic elements to it as well?
So we use Megatron as sort of a framework for training very large transformer models. They could be GPT-3 style models, they could be BERT style models, or T5 style models. All of those, sort of encoder decoder models. Those models can all be trained using Megatron. I think of Megatron as kind of like a demonstration vehicle to show the world like what can be done with a big, huge GPU cluster for language modeling. But there's lots of different kinds of language models, not just GPT style models. Now we have trained some pretty big BERT and GPT models over the years. And sometimes we'll submit to various leaderboards. For example, we were at the top of the race leaderboard for a while with a Megatron BERT model. And it was basically just a standard BERT model, just much bigger. And also we changed the ordering of some of the residual connections in the model because we found that the standard BERT ordering couldn't optimize at scale, whereas switching to more of a GPT style ordering of those connections actually allowed it to optimize. So, but I would say it's still essentially a BERT model, just tweaked slightly. So our goal with Megatron hasn't been primarily to invent new kinds of language models. It's been primarily to show people the most efficient way of training language models that they're interested in, and then also building up our capabilities internally at NVIDIA about what language models we have access to and what language models we can use for our own internal purposes. And so that's kind of been the goal of the project.
Got it. And so you rattled off a whole list of areas where innovation was required, kind of all up and down the stack, in order to deliver on your goals for Megatron. But you started out by saying that the key thing that was missing was kind of software. And I'm assuming there's an element of system level software that was required. And I'm wondering if you can kind of go into what were the key elements of that, and what is the basic approach for distributing a large language model on the infrastructure that your target infrastructure, in this case, the DGX pods?
Yeah, great question. So there's a lot of stuff that goes into it. I think starting with Megatron itself. So Megatron provides 3 different kinds of parallelism to train these models. First, we have what we call tensor parallelism, and that's where you take each of the tensors that comprises the model and shard them across GPUs. And that has some really nice properties because it doesn't affect the optimization algorithm at all, right? Like we're still executing the model exactly as normal, and the optimizer doesn't really need to know about anything that's different. It's just running faster. The sort of challenge with tensor parallelism is that you need a lot of small, low latency messages to be sent between all these GPUs because you've sharded the model across them. And so they have to communicate frequently in order to sort of process each layer as you push data up and down the stack of the model during the optimization. And so we tend to use tensor parallelism at the sort of lowest level of the box, so like inside of a node. And a node might have 8 GPUs in it, so we might go 8-way tensor parallel, splitting the model across 8 GPUs inside the node. And then, our GPUs inside of DGX nodes are interconnected using NVSwitch, which is an extremely high-speed, low-latency switched fabric that allows all of the GPUs to access each other's memory, directly. And that enables us to, move data between the GPUs quickly enough to make tensor parallelism profitable. Mm-hmm. So that's the first kind of parallelism that we provide. The second kind of parallelism is what we call pipeline parallelism. So this is also another form of model parallelism where we take the layers of the model and we assign them to different nodes. And so the idea is that when you push data through a model, it's going to go from one node to the next, kind of in a pipeline fashion, and then during backprop, it's going to flow the opposite direction through the pipeline. Now, pipeline parallelism is really great in the sense that the communication requirements aren't very large because you're basically cutting the model at layer boundaries, and you just have to move activations between the boxes as you're doing this optimization. However, pipeline parallelism does affect the optimization because if you just do this sort of standard optimizer thing of like push, a batch of things through the pipeline, you're going to have bubbles in the pipeline. For anybody that has studied pipelining in computer science, you'll know that pipeline bubbles mean you're not actually getting parallelism. You have all this potential parallelism, but you have all these nodes that are sitting there idle, sort of waiting for a job to come from somewhere else in the stack, right? Mm-hmm. And so that obviously means it doesn't scale unless you fix that somehow. And the way to fix that is to use micro batching, where you take your mini batch and you break it up into even smaller pieces, and then you schedule those so that you can overlap as much as possible with all this pipelining. And we've actually been working on the scheduling for this. It's not a trivial problem. There's a lot of trade-offs to make, and they each have a different space in this sort of latency bandwidth demands that you're placing on the interconnect. And so, we spent a lot of time optimizing the algorithms that we use for scheduling pipeline parallelism, and that brings some pretty significant speed improvements to Megatron.
When you start, before you get to the next aspect of parallelism, when you start talking about pipeline parallelism and changing the way batching is done, in addition to the impacts that you mentioned at the infrastructure level, do you also see impacts at the model level, meaning changes in the way the model converges and performance and all those things that we associate with tweaking batching parameters?
Right. It depends. So what we typically do is we choose a pipeline schedule that actually still obeys the semantics of the model. So you could imagine running a pipeline schedule that sort of loosens some of the synchronization constraints and then allows kind of the model to operate on maybe some stale weights during some parts of the optimization pass, and that could increase the parallelism. It also would change the optimization algorithm, right? Because now you're not really implementing an atom or a stochastic gradient descent style optimizer. It's now kind of a little fuzzy. It's a little muddy. What exactly are you doing, right? So we don't recommend that at the moment. That's not how we've got our best results. Our best results with pipeline parallelism we have been achieving when using something that is semantically equivalent to not using pipeline parallelism. However, you're 100% correct that it does have an impact for the batch size, right? And the third aspect of parallelism, of course, is data parallelism. So to this question of how big of a batch can you run the model at? If you have an infinite batch, then you have infinite data parallelism, and then you can use some of that data parallelism to create more micro batches, which then reduces your bubbles for pipeline parallelism, and that's fantastic. But of course, we don't have infinite batch sizes because our optimizers don't function that well at super great batch sizes. And so, we typically think about the data parallelism as kind of a budget that we're going to spend. And we might spend that budget on traditional data parallelism, sort of, spreading the mini batch across many nodes. Or we may spend some of it on micro batching to improve pipeline parallelism. And that's part of the trade-offs that we examine with the Megatron code base when we're looking at training a particular model on a particular set of hardware.
Hmm. Hmm. And when you talk about the trade-offs that you examine, um, is there, do you have, I guess I'm trying to get at like an abstraction of the things that you've learned. I'm imagining that, um, what you have done with Megatron for large language models, you will do for other models, or might want to do for other models, meaning you've got, um, you've got this kind of continuum of ways that you might want to scale a model. The first is just kind of you scale up running on a bigger, GPU or something like that. Then you might want to use like an off the shelf distributed um, tool like a Horobot or something like that. And I'm thinking of what you have done with Megatron is kind of go very deep and tailor it to a specific class of models,
That's right.
and a specific set of infrastructure.
That's
And you might want to do that for other, you might want to do that, across different types of models and different types of infrastructure. And I'm wondering if there's some abstracted set of learnings from this, exercise in this project that would guide someone that wants to do something similar for another type of model or another type of infrastructure.
Yeah. NVIDIA thinks of our work as accelerated computing, which means optimizing full stack from the application to the framework to the libraries and compilers to the GPUs, the interconnects, the systems that it all goes in. And, Megatron is an instantiation of that for
Mhm.
large language models. So it has a lot of, we've talked about some of the pieces. It has a lot of work also in kernels, that are running on the GPU to fuse things together to use memory bandwidth more efficiently. We've worked very closely with the Nickel team that builds communication primitives for the GPUs so that they are able to support really efficient communication in the exact patterns that we need for large transformer models on big GPU cloud HPC style infrastructure. So, it is kind of a collection, and it kind of spans a lot of different kinds of technology, right?
Mhm.
So as far as like the lessons that we learn from that, I think to me it's part of our philosophy here at NVIDIA that we are going to consider the problem um, full stack, and we're going to optimize it all together. We're going to pick things that are important, right? Things that justify this kind of investment. I think language modeling is a really good example of that. It's something that's important enough to so many people that it's worth, jointly optimizing everything from the algorithms to the GPU itself to make it more efficient for something like this. So that's kind of the highest level takeaway that I'd get from it. I guess maybe some other takeaways is that GPUs scale really well. Even at the scale of many thousand GPUs training a single model, that we're able to sustain 52% of the theoretical peak of the machine. I think that's a good sort of speed of light guidepost for anybody doing this kind of work, that they should expect to be able to reach that kind of efficiency with enough optimization. But again, doing that, you can't just work on one piece of it alone, right? They all have to be considered jointly.
Do you have a sense for if you wanted to, exceed that 50%, like where the next level of gains, well, how close do you feel like you are to a theoretical ceiling? And if you're not, fully there, where does the next set of gains come from?
Yeah, well, the theoretical ceiling is 100%, and we're at 52%. So we know exactly where we are with regards to the speed of light. Now, getting to run anything at the speed of light, the arithmetic peak throughput of a large supercomputing machine is extraordinarily difficult. And ordinarily, I declare victory whenever we get to 50% because from there on out, it's diminishing returns, right? There's only a factor of 2x that we have left to give, even if we applied infinite effort. I think it's reasonable. We might continue improving it from 52% to 55 or maybe even 60%. That would be fantastic. And, we're working with teams across NVIDIA to see what we can do about that. The other sort of interesting part about the work that we get to do at NVIDIA is that we get to change the GPU itself. The GPU is a chip designed for particular workloads. This sort of mindset of accelerated computing means that we change the GPU every generation and we optimize it for the things that we think are going to be important in the future. And I actually report, so my whole applied deep learning research team sits inside NVIDIA next to the teams that are building future GPUs and the architects that are trying to optimize the chips themselves. And so we work really closely with them so that we can make the chips of the future perhaps even more optimal for these kinds of workloads.
What are the features of a future GPU that would be more optimal for a Megatron style workload?
We're always working on the tensor cores themselves. So, GPUs since 2017 have sprouted custom arithmetic hardware for deep learning. It's very arithmetically dense. They're kind of little tensor processors, we call them tensor cores, that are embedded inside of the GPU and used to do the computationally intense parts of deep learning. And there's always things that we'd like to do to improve them, to make them more efficient and more flexible. And often that involves the arithmetic work itself. Sometimes it involves the memory infrastructure. So all of the caches and various buffers inside of the chip that are moving data around, they have to work at peak efficiency in order to keep the tensor cores fed. And so that's also a really interesting area of ongoing work. And then, I think that these days we're also very excited about system level issues, right? So not just the chip, but how do the chips communicate? So we have this NVSwitch fabric. We would like to make that even better. We would like to allow more GPUs to communicate over that fabric, make it lower latency, make it higher bandwidth. We're thinking about how do we improve the GPU for this kind of workload, not just with each GPU, but also kind of at the data center level. Like how are we going to co-optimize all of the hardware in the data center to make applications like large language modeling really sing?
Mm-hmm. Are there I guess there are a couple questions, like are there things that you've learned with Megatron that you see scaling down to less less large scale deployments like the DGX pods? And maybe another angle to that is there a play for, or an element of the use of techniques like quantization or compression that you look at in connection with this project?
Yeah. Well, looking at memory bandwidth is always really important when optimizing kind of low level details of some software like this. And that's important at large scale. It's also important at small scale. What that often involves is kernel fusion. We're big fans of the PyTorch JIT. So Megatron is written in PyTorch, and we've been able to use the PyTorch JIT to great effect in order to improve our memory bandwidth usage. We also have written some custom kernels in CUDA directly to handle cases that we really needed to optimize, and I think that's fairly common in this type of work. Many projects that I've done over the past 10 years that have been in this space have involved writing some custom CUDA, and it's really great when you have a processor like the GPU that's programmable enough to allow you to write the sort of glue logic that makes the optimization happen. It's not just a big tensor crunch, but there's all sorts of stuff in the optimizer, and there may be transcendental functions, and all of that you can write in CUDA, which is really easy to do, and that kind of optimization can really be important. It's definitely been important for Megatron. I think it is important for smaller scale things as well. Can you remind me of your second question?
The two questions were kind of, learnings that scale down and compression quantization.
Oh, that's right. Compression and quantization. This is ongoing work. We're big believers in compression and quantization at NVIDIA. Our tensor cores support various forms of quantized arithmetic. 8-bit multiplies with 32-bit adds integer, for example, but also 4-bit, 2-bit, and even 1-bit. Of course, the throughput on 1-bit is extraordinarily high. However, maybe it's harder to use, right? So we don't typically see people deploying models with 1-bit 1-bit multiplies, but nonetheless, it's all there. So we definitely look into that. Quantization for very large language models, in my opinion, is still an unsolved topic. There's a lot of people working on it because deploying these models is important. That's why we're spending all the effort training them. But then, of course, if we can reduce the cost of deploying them, then they can be much more accessible. And so quantization, I think, is a big part of that. Right now, Megatron does not have any recipes for, let's say, taking a pre-trained enormous language model and quantizing it to 8-bit multiplies, for example. I think in the future that would be fantastic if we could provide such a recipe, because I think that would be useful. But I think research is still ongoing to figure out exactly the best way of quantizing these very large models. I do know that people are doing it, so it is a realistic thing to do, but it's not a trivial thing to do. Sort of the standard thing of just quantize it and try it doesn't usually work very well. As far as compression goes, we also are excited about compression at NVIDIA. Ampere, our most recent GPU generation, actually has an interesting sparse matrix instruction that doubles the throughput of the GPU, both for floating point as well as for integer data types, with the restriction that out of every 4 multiplies, you get to pick 2. And you can pick them arbitrarily, so it doesn't have to be the same 2. For every block of 4, you're going to provide a bit mask that tells the hardware what to do. And but the structure is out of 4, choose 2. And I think that's kind of an interesting primitive. It has a certain amount of restriction, but also a certain amount of flexibility. And it's ongoing research to figure out exactly how to use that best, specifically for deployment. I'm most optimistic about using that capability for inference of these very large language models.
Yeah. You mentioned early on kind of these 4 pillars or silos that you and your group play in. One of those was graphics, and another project that you've been working on in that space is DLSS.
That's right.
Can you tell us a little bit about that project, deep learning supersampling?
Yeah, so this has been great fun to work on over the past few years. NVIDIA decided to ship tensor processing units to inside of the GPU to consumers around the world. So these days, if you are a gamer and you have an RTX GPU, you've got tensor cores, and there's an enormous amount of AI throughput just waiting to be applied to new things. And in this case, we thought, well, how about we figure out what we can do for graphics? Sort of the original start of the GPU. And it turns out that we've been able to come up with a reconstruction method that runs in real time that is essentially doing a sparse rendering algorithm. So you render at lower resolution, let's say 2 to 4x less samples. So you're reducing the amount of normal GPU work by 2 to 4x. And then at every frame, you're going to reconstruct a high resolution output frame by using a combination of the last frame as well as some data that the games compute during the process of creating the 3D environment, as well as the inputs, the low resolution inputs from the current frame. And you feed all of those into a neural network and ask it to do reconstruction. And even though it takes a certain amount of time to run that reconstruction, we can still provide enormous speed boosts because we've been asking the GPU to do 2 to 4x less work, and then we essentially just have a smarter rendering algorithm that's able to generate very high resolution, very detailed videos with fewer samples, because this reconstruction method is just much more powerful than traditional ways of rendering graphics. And so essentially what this does is it makes a small GPU look like a big one. And that's really exciting to a lot of our gaming customers, as well as our professional customers, especially with the advent of ray tracing. So, NVIDIA has been working on redefining real-time graphics using ray tracing and specialized hardware for ray tracing, part of our accelerated computing philosophy, right? So we're looking at graphics full stack, optimizing it. We've added all sorts of hardware for ray tracing. And, we're really excited about how that's making games look better and how that makes professional design applications much more realistic, but it's extraordinarily expensive computationally. And so it kind of goes hand in hand that, at the same time we're dramatically increasing the compute burden on a GPU, we're also making the GPU smarter by using deep learning in real time as part of the rendering algorithm. And so that, I think, has been a fantastic combination that people really enjoy.
Got it. And when you, can you talk a little bit about the development of the model and what kind of training data you're using and architectures and things like that?
Yeah. So let's see. We are using a convolutional autoencoder for the model itself. I would say it's not particularly exotic, the model itself. It's kind of maybe what people might expect. I think that the work that has gone into DLSS, and it's taken many years to make it good enough to be useful for people. In fact, the first version of DLSS, I think it was a really brave step, sort of the from 0 to 1 kind of thing. Like, we're going to use real-time deep learning for graphics, and no one's ever done that before. But I think there are a lot of well-documented challenges with the first version of that technology, and so we reinvented it completely for DLSS 2. The interesting thing is that the neural networks are quite similar between 1 and 2. They're both convolutional autoencoders. And as often happens when applying deep learning to a real product, a lot of the work is in the data sets and in the application framing. So sort of the definition of what are the inputs and the outputs to this neural network, what are we asking it to do, and how do we make it safe to use when it messes up?
Yeah.
As every machine learning technique is going to mess up, but we want the overall application to still be providing value. So we've invested significantly in data sets to make DLSS 2.0 generalized. So we only train this model once on completely synthetic content that we have generated ourselves, and then we apply it to, at this point, more than 50 different computer games and professional applications. They all can run using the same model. That's only possible because of all that work in the data set construction and in the sort of application framing, the not deep learning stuff that makes it actually come together.
Got it. And did you say it is only applied in a kind of a prescribed subset of games that it's kind of known compatible with, or is it a general utility that is available in the GPU?
It needs to be integrated directly into a game. We rely not just on the sort of game to render itself at a lower resolution, but we also rely on inputs. We call them motion vectors. It's basically the game is rendering things in 3D space, and so it knows about where the objects are, and we need it to tell us information about how things are moving around in order to do this reconstruction very, very precisely. So that the game needs to provide that, and so the game needs to be aware of DLSS happening and needs to call the DLSS library in order to do that work and provide it with the proper inputs. And it also needs to be integrated at the correct point in the graphics pipeline. So graphics, there's the sort of main rendering where you're reasoning about the 3D environment and what it looks like, and then after that, at the end, there's this step called post-processing where you add things like the user interface and effects like chromatic aberration or motion blur. These kinds of effects make the game look like more filmic, perhaps, but they're terrible for AI reconstruction because they're adding a ton of noise that is very specific to the art of a particular game, and is hard to generalize across. And actually, it may quite distort the image. Like you can have lens distortions so that the edges of the frame aren't straight. And it's much too hard to ask AI to learn about all of the different kinds of post-processing effects. It's much better for the game because they're not expensive. They're not that expensive anyway. So it's much better to ask the game to put DLSS in the appropriate part of the rendering pipeline and then do its own post-processing effects at full resolution so that your UI is super sharp and all of these filmic effects look exactly the way the artistic director intended. It's much better to do that than to try to apply DLSS outside of the game. And so it does require integration, and that's why it can only run in specific games where it's been integrated. However, we have made a lot of progress recently in getting DLSS in the form of a plugin that game developers can just use if they're using some of the standard game engines like Unreal Engine or the Unity game engine that a lot of people use to build games. They can just use the DLSS plugin, and all of that integration work is handled kind of at the game engine level, so game developers don't have to do it themselves.
Nice, nice. And in terms of the training data, you mentioned that it was synthetic data that you created. Is the general idea that you create a full resolution and then downsample it and train the network on pairs of those images?
Yeah, that's very close. We actually create our data set at 16K resolution. So
Oh, wow.
so a 4K image has 4,000 pixels across the top. A 16K image has 16,000 pixels across the top. So it's essentially 16 times more pixels than you would expect in a 4K image. And so rendering something at 16K resolution is very slow, and it happens offline. We actually have a big supercomputer that's constantly just running synthetic data creation, because as you know, with any sort of machine learning product, you're constantly improving the data, right? Improving the data is one of the most important ways of improving the final product. And so we're constantly improving that data set. We're constantly finding errors in it and re-rendering it. So we render it at this very, very high resolution offline, and then we also render it at the lower resolution that we're going to expect the game to be running at. And then those form the inputs to our training pipeline.
Got it. And why 16K? The games aren't rendering at anything close to 16K.
Yeah,
Even
well,
their final resolution, not as opposed to their kind of reduced resolution, right?
that's right. We actually find that our neural reconstruction method is able to learn information about how objects should look at this very, very high resolution, and then use that to make games look better, even when rendered at low resolution. And one of the reasons that this happens is because of an effect called aliasing. So when you take the world and you discretize it into pixels, sometimes you can get lines that have sort of a stair-step effect. And when those lines move, like as an object moves through space, that stair-step effect starts to look like crawling lines, like the edges of objects flicker and they kind of crawl and swim a little. And this is called aliasing. And one of the ways of improving aliasing is if you just render with like way more samples and then combine them, sort of with a filter to sort of blur them together to make a lower resolution image, then you actually have like a closer sampling of the ground truth image than you could get if you just rendered at the lower resolution. And so that's like a standard approach to anti-aliasing. We want our DLSS network to learn both the super resolution problem as well as the anti-aliasing problem, so that the resulting videos that we create are both very detailed, but also don't have a lot of aliasing to them. And so we're trying to learn this problem jointly, and that's why we make the training data so large.
Mm-hmm. And do you find that, or do you ever find that there are games whose kind of look is just so far out of distribution with your synthesized data that it, even if they're putting it in the right point in the process, it just doesn't work very well? I'm trying to get at how
Yes.
sensitive the game is to the training data set.
Yes, absolutely, and that's why we're constantly improving the training data set
Yeah.
and adding more data to it. One of the examples of this has to do with particles. So in video games, there's often like dust or sparks that are flying around, or rain. These kinds of small moving objects are really important to the feel of the game, and sometimes actually to the playing of the game, right? Like if for example, you're shooting a laser, sometimes those lasers are rendered as particles. They don't actually have geometric information behind them. So when we ask the game to provide geometric motion vectors to tell us how objects are moving very precisely in order to do this reconstruction, we know that those motion vectors are not going to cover all of the important objects that you see. And particles are one of those. And so what does this mean for the reconstruction? Well, if the reconstruction wasn't expecting particles to exist, it might just erase them. It might just think this is an aliasing artifact because we're rendering at low resolution. That little sparkle, it's not a raindrop, it's just an aliasing artifact, and I'm going to delete it. And so, getting particles correct with these reconstruction methods is challenging, and it's one of the things that our model has to learn. It needs to learn the difference between aliasing artifacts and particles that actually need to be preserved. And so, that's one of the things that we work on in our synthetic data sets, is exposing our models to the right kinds of particles so that they don't erase them. And another thing that we've done a lot has to do with moire. So moire, perhaps you're familiar with this. If you look through like a screen door, sometimes objects can have this kind of like pattern to them that kind of has like lines at different intervals that kind of get closer and farther apart. The moire effect is often seen when rendering gratings at a distance, where you have like small thin objects that are next to each other. And you can start to get this this pattern that emerges, and it's very undesirable. People don't want to play video games with like moire patterns flashing at them, and so that's another thing that we've trained the model to see and then to avoid reproducing. So all of that, that kind of work is really important in the synthetic data set for DLSS.
You mentioned the motion vectors that you expect the game developer to provide. Is there an implication in there somewhere that the network or the process is somehow selective in the super sampling, or that it is, there's some element of attention where it's learning where the objects are, and those are rendered more, it places more of its emphasis there versus the background? Is there any element to that?
Yeah, for sure. Absolutely. I mean, that's what we're asking the network to do, really,
Yeah.
is the motion vectors. So so the motion vectors tell us how objects are moving, and you can imagine how useful that is for reconstruction, because part of the benefit of a temporal reconstruction method is that you can use samples from prior frames, right? And so the motion vectors are going to tell us how the samples from prior frames are going to move into the current frame. And so then we can decide whether we want to use that sample or not for the current frame. Now, the issue is that just because something is moving geometrically doesn't mean that its appearance is moving geometrically. For example, if you have shadows or lighting effects or reflections, the way that the object might be moving might be anti-correlated with its appearance, or its appearance may not be moving at all, right? Like if you have an object that's moving into shadow, you don't want to drag, sort of the bright object that's lit into the shadow and like ruin the edge of the shadow, right? So some of the geometric information that you're getting is useful, and some of it is actually the opposite of useful, right? And so this is kind of an interesting problem for machine learning to figure out, because it's very difficult to write down the rules as a human for how to do this temporal integration problem, sort of human heuristics. People have been writing heuristics to do this for many years.
Yeah.
And they get better and better, but it's actually quite a challenging problem, and so that's sort of the value of machine learning, is that we just learn the heuristic.
Do you think now that this is in the hands of developers and you're getting these data sets with the motion vectors, that maybe a future approach would be to train a network kind of multitask to both do the super resolution and predict the motion vectors against the data that you've collected? Do you think that might work?
Absolutely. Yeah, absolutely. And that might, for example, make the process of integrating DLSS into a game easier, right? If for whatever reason a game found it difficult to create the motion vectors, well,
Mhm.
perhaps we should just learn those motion vectors. I mean, this is very closely related to the well-known optical flow problem in computer vision.
Mhm.
And not uncoincidentally, my team at NVIDIA has been working on optical flow for quite some time, because it is so core to a lot of the graphics problems that we care about.
Yeah.
So yeah, it's absolutely something that we consider, and this is the kind of thing that we get to play around with as we reinvent graphics with artificial intelligence. Figuring out like what parts of traditional graphics we're going to keep and what parts we're going to replace with real-time deep learning is exciting research.
Awesome. Awesome. Bryan, I suspect there's a ton more fun things you're working on that we could continue talking about, but I just wanted to thank you for joining us and spending some time sharing a bit about those couple of projects.
Of course, it's my pleasure, and it's really nice to tell the story a little bit about how NVIDIA is thinking about AI and how we're starting to use it for our own products. And I expect there's going to be lots more exciting things in the future to talk about as well. So thank you.
Awesome. Thanks so much.